Hi, I'm Dr. Incognito. In this video, we're going to discuss linear transformations. So first, suppose V and W are vector spaces. Then a linear transformation, L, from V to W, is a transformation that has the following two properties. 1, L of lambda V is equal to lambda times L of V, where lambda is any scalar and V is any vector in the input space, capital V. 2, L of V1 plus V2 is equal to L of V1 plus L of V2. This is for any V1 and V2 in the input space, capital V. So basically, a linear transformation has these two properties, and just a transformation in general is like a function. It's got an input, let's call the input V, and then an output, L of V, which would be in W. So it's got an input V and an output L of V. So it's like a function. The word function is usually reserved for transformations which have an output which is a real number. So if this space happened to be R and the input space happened to be R, then we would have a function of one variable. To make the function linear, it would have to have these two properties. So a linear transformation, we allow the input space to be a little bit more general than just R. It can be any vector space. And the output space, instead of being R, can be any vector space. So a transformation is like a generalized function. And a linear transformation in particular has these two properties. L of lambda V is equal to lambda L of V, and L of a sum is the sum of the L's. So the first one is saying, if we're going to scale a vector, we can scale the vector first and then apply the linear transformation, or we can apply the linear transformation first and then scale, and we get the same thing. And the second property is saying that we can add two vectors and then apply the linear transformation, or apply the linear transformation to each vector and then add them together, and we get the same thing. So the order in which these things are done, we can think of these as being geometric things. Scaling a vector, that would mean magnifying or contracting it. And here, adding two vectors. We can add them and then transform, or transform them and then add. For a linear transformation, the order in which these geometric operations are performed does not make a difference. Let's look at a simple example. Let V be R2 and let W be R2 as well. So we'll make a transformation from R2 to R2, and we will discuss whether or not it is linear. And let this be defined by L of a vector xy equals the vector negative x, y. So that's our transformation. Take a vector in R2, x, y, and transform it into negative xy, another vector in R2. So for example, L of the vector 3, negative 5 is the vector -3, -5. This particular example has a nice geometric interpretation. If we take any vector v equals xy, then L of v will be the vector -xy. It will have the same y coordinate and opposite x coordinate. So you can see that L is a reflection transformation. It's a reflection, in this case, in the y-axis. So our transformation here is a reflection, a nice geometric interpretation. And this is, in fact, a linear transformation. Let's verify that it's a linear transformation by showing that properties 1 and 2 hold. So property 1, let xy be any vector in R2 and lambda be any scalar, then L of lambda xy, let's compute this, and let's decide if it's equal to lambda times L of xy. So first, let's multiply lambda inside the vector, multiply the scalar times the vector, so it will become lambda x, lambda y. Write that again. Lambda x, lambda y. Now, L of a vector, the rule is we take the negative of the first component and leave the second component alone. So negative lambda x, lambda y. And now we can factor out the lambda. So this is lambda times negative x, y. And lo and behold, the vector that we see here is the vector L of xy. So this is equal to lambda times L of xy. So property number 1 has been satisfied. L of lambda xy, if we scale the vector first and then apply the transformation, that's equal to lambda times L of xy. Apply the transformation first and then scale. Now let's check property number 2. So let xy and x prime, y prime be in R2, our input space. Then L of the sum xy plus x prime, y prime is equal to, so in order to know what to do, we should have a single vector in the parentheses here. That's why in the first step in the last computation, I moved the lambda inside the brackets of the vector. So I'm going to do the same thing here. I'm going to combine these two vectors into a single vector by adding them. This is L of the single vector. You add them component-wise, x plus x prime, y plus y prime. So that's our input vector. The transformation tells us to take the negative of the first component, so negative 1 times the sum, x plus x prime, and then leave the second component alone. And now I would like to distribute this negative, and I would like to split it back into two separate vectors. Like we see here, two separate vectors added together. So this is equal to negative x minus x prime for the first component, and y plus y prime for the second component. I'll leave this here. This is equal to now negative x, y, plus negative x prime y prime. So this is L of the first vector, v1, if that's v1, plus L of v2 would be here. So this is L of the first vector, xy, plus L of the second vector, x prime, y prime. So both conditions 1 and 2 were satisfied. And so the transformation, the reflection in the y-axis transformation, is indeed a linear transformation. Let's look at another example of a transformation from R2 to R2. Let's consider the transformation L from R2 to R2 defined by L of xy equals x plus 1, y plus 2. So geometrically, what's going on here is given any vector xy, if that's v, then L of v is obtained by shifting the terminal point of the vector to the right by 1 unit and up by 2 units. So over 1, up 2. So the vector whose terminal point is here, x plus 1, y plus 2, and whose initial point is the origin, this would be L of v. So this one's v, and this one is L of v. We can take a look at this and we can write it as xy plus 1, 2. So essentially this linear transformation is taking a vector and adding the vector 1, 2 to it. This would be considered a translation by the vector 1, 2. So is this a linear transformation? Is L linear? And the answer is no. For a linear transformation, L of the 0 vector will always equal the 0 vector. So in this particular example, L of 0, 0, that's our 0 vector in R2, is equal to 1, 2, which is not, obviously not, the 0 vector. So this cannot be a linear transformation. It was a little bit presumptuous then to call it L. Maybe we should have just called it T for transformation. But anyway, L is not linear. Okay, so there's a little look into linear transformations. Thank you for watching.